Hello everyone, today we'll be discussing the theoretical concepts related to the chapter work, energy and power. These concepts will build your fundamentals which would be necessary in solving the problems which we'll be discussing later on, and similar kind of problems will be asked in your engineering entrance examinations as well. So let's begin with the theory.
Hi. Now we deal with work, power, energy. First, we deal with work. In general terms, what do you define like work? Pushing a car, moving a heavy sofa, taking a stack of books from one floor to another floor. All these example agrees with everyday meaning of work. They have something in common. In each case, you do work by exerting a force on a body while that body moves from one place to the other that undergoes a displacement. You do more efforts if force is greater or displacement is greater. To quantify this effort, we introduce a new term called work. We define the work W done by a force as the scalar product of force and the displacement. As we know, force and displacement is the vector. The scalar product of the force and displacement we get as Fs cos theta. Work is thus as a scalar quantity, and by Fs we get the unit as Newton meter. Okay, now just we see the ways of doing work, like pulling a block, pushing a block. These sort of works can be done in a different ways. So if suppose a block is pulled at an angle of theta and it has moved a displacement of s, so work done by the block will be equal to F into S into cos theta, because we know work is scalar product of F bar and S bar, and the angle between the F bar and S bar is theta. Here we will be getting Fs cos theta. And there are forms of work like positive work, negative work and zero work. If suppose we pull a block from front, the angle between force and displacement is less than 90 degrees. So work done will be a positive quantity, Fs cos theta. Work actually is an Fs cos theta. So in this case, while pulling a block, theta is less than 90 degrees. So thus work done by the body by us will be a positive quantity, and negative quantity if we consider. So if the force is being applied in this direction and the body is moving in this direction, the angle between them is greater than 90 degrees. In this case, F is equal to Fs cos theta, and we know if cos theta in cos theta, if theta is greater than 90 degrees, we get it as a negative term. So the entire quantity Fs cos theta will be a negative term. In this case, we mention it as a negative work. And zero work. Suppose if we are catching a string and it is having a bob. If we squeal the string and the body moves in a circular direction, in this case the centripetal force acts in the radially inward direction, and the displacement at any instantaneous displacement ds is perpendicular to this. So work done at this position will be equal to Fs cos theta. Here as theta is equal to 90 degrees, work done will be equal to 0. So now let us move to the next slide. Now let us see how work affects the path travel. Initially we saw the angle between the force and displacement is a different thing, and now here we consider the displacement and force according to the path travel. First let us consider in the case 1, force acting on a particle is constant and path is zigzag. Let us consider it in this direction. The path is in this direction, and the force is always is equal to the F I cap. Force bar is always equal to the F I cap, and the path traveled by the particle is in this direction. Let the initial position be A and the final position be B. So displacement of the particle is in this direction from A to B. Let us consider at any instant C, the displacement vector will be in this direction ds bar, and the force will be is equal to F bar. Here also the force will be F bar this direction, here also it will be in this direction. So work done here, what we will be doing is like integrating each instance of time, that is integrating F bar dot ds bar. As force is a constant direction, we just integrate the ds bar. This ds bar we will be getting the displacement of the particle, F bar dot s bar ab. This is just the displacement. Now we consider one of the forces acting on the body is constant in magnitude and direction and is always along the velocity. Before this example we have seen force is in a fixed direction and the velocity is varying. Now let the path traveled by the particle be this direction and the instantaneous velocity is this direction, and it is given force is constant in magnitude and always in the direction of velocity. So force also will be in this direction. At any point it will be a similar case. If suppose here the instantaneous velocity is this direction and the force also will be in this direction. So while going to the formula wise, work done is let this point be A and this point be B. Work done from point A to B is equal to integral F bar dot ds bar. In this case, as theta is always equal to 0, cos theta will be is equal to 1. So work done by the system in this case will be is equal to F into S. S is not the displacement, it's the distance travels by the particle from A to B. If suppose force is perpendicular to the displacement at any point of time, that is, it is a circular motion, force will be always is equal to the centripetal force F bar and the displacement vector is always is equal to the ds bar perpendicular to this. In this case, work done is equal to integral F bar dot ds bar and theta is equal to 90 degrees. We know cos theta is equal to cos 90 degrees is equal to 0. So work done will be always is equal to 0 when force and displacement vector are perpendicular to each other. Yeah, up to now just we have seen for a particular path whether the displacement is perpendicular or it is along the direction or everything. If suppose in the JEE problems generally what we get is they will be giving a graph and asked to find the work done. So in this case, work is the area under the graph and that is equal to W is equal to integral F bar dot ds bar. That is, if a particle is moving from particle A to particle B in this direction, the work done by the particle in moving from point A to B is the area under the graph. This will be the work done by the particle. Yeah, now we deal with energy. What energy is? Practically any work can be done by using energy. Example, running, reading, lifting a stone. Even for instances like sitting, eating, sleeping, we need energy. So, but according to physics, capacity to do work is defined as energy. Energy is quantity that can be converted from one form to another form but cannot be created nor destroyed. The total energy, that is the sum of energy present in all forms, always remains same. No exception has been found up to now. Energy is basically in many forms: mechanical energy, thermal energy, chemical energy, electrical energy, magnetic energy. Here basically in our chapters we deal with mechanical energy. So mechanical energy is basically of two kinds. One is kinetic energy and other is potential energy. First we discuss with kinetic energy. What kinetic energy is? A dancing, running man is said to be more energetic compared to a sleeping, snoring man. In physics, a moving particle is said to have more energy than an identical particle at rest. Quantitatively, the energy of the moving particle over and above its energy at rest is defined by kinetic energy. For suppose, if a body of mass m is moving with a velocity v, then kinetic energy of the particle is defined as half into m into v bar dot v bar. As in this case v bar it is a scalar product, and as in this case cos theta is equal to 0, we get kinetic energy is equal to half mv square. By this we will be getting kinetic energy as a scalar quantity. Kinetic energy of an object is the measure of work an object can do by the virtue of its motion. So according to this, we will be getting kinetic energy of a system is scalar addition of all kinetic energies of the particles. Yeah, now let us look into the work done by the conservative forces and non-conservative forces. First, let us look into conservative forces work done. Conservative forces. So work done by the conservative forces is independent of the path travel, but it depends on the displacement, that is positions of the particle. For example, if we take work done by the gravity, do you feel how? So let me just explain it. Force on the body by the gravity is, let us take the force vector by the gravity is equal to minus mg j cap, because it will be acting in the downward direction. Let the body has been moved from point r1 bar to r2 bar with the frame of reference of the earth. Now please note this, with the frame of reference of the earth. Frame of reference of earth. So let r bar initially be equal to r1x I cap plus r1y j cap. R2 bar is equal to r2x I cap plus r2y j cap. First, let us assume the particle has been moved from the point A to point B. Point A is r1 bar and point B is r2 bar. So let this path be 1. So work done by the gravitational force is equal to r2 bar minus r1 bar. This is the displacement, so we take r2 bar minus r1 bar. This is equal to minus mg r2y minus r1y. So by this equation, what we can generalize is work depends on the position. If the particle has been moved from the point A to B, not in path 1 but it has moved from path 2, here also we will be considering the initial and final positions of the particle. So it basically depends on the initial and final positions of the body irrespective of the path travel. And here from this equation we can generalize this as work done by conservative forces will be always equal to the negative of mg r2y minus r1 by. Actually, in the later section we will be dealing with the potential energy mg into the displacement in the position. We generalize this as potential energy. So this is equal to negative of the potential energy. Work done by the conservative forces is equal to the negative of the potential energy. We later discuss what is potential energy. So now let us consider about the non-conservative work done. Work done by the non-conservative forces. Work done by the non-conservative force is dependent on the path followed. For example, frictional force. As frictional force is a non-conservative force, the body has been moved from point A to B and it has traversed a distance L. So the work done by the frictional force will be equal to F into X. So this is X is the displacement of the particle. X is the displacement of the particle. So work done by the frictional force is equal to the F into X. This actually can be generalized in a different way. First, suppose the particle has been moved from point A to point B in this direction. This is path 1, and let us take part 2 as particle initially has moved from point A to point C, and then particle has moved from point C to point B. In this case, work done from A to B is not equal to work done from A to B in part 2. Because as taken, frictional force is a non-conservative force, it takes the displacement for work done. So the displacement from A to B is not equal to the distance travelled by the particle from A to C and C to B. So work done by the non-conservative forces depends on the path followed, and we know that in the given in the obtained situation, work done does not have any potential energy term. So non-conservative the work done by the non-conservative forces does not have a potential energy term, but work done by the normal force is always equal to 0, though it is a conservative force. Let me give a small hint to find the system is conservative or non-conservative. If at all we have dou of F bar is equal to 0, then it is a conservative force, that is dou of dou x by I cap plus dou of dou y by j cap into F bar. This is the cross product, should be equal to 0 bar. If at all we get this condition, then the force is a conservative force, or else it is a non-conservative force. In work energy power chapter, the basic thing we actually deals with is work energy theorem. So what it states is work done by a particle by a resultant force is equal to change in the kinetic energy. Let us just write this: work done by all external forces. Put this in this way: work done by all external forces will be equal to the change in the kinetic energy. So work done by the all external forces include work done by the conservative forces and work done by the non-conservative forces. That is equal to the change in kinetic energy. That is equal to KEF minus KEI. Final kinetic energy minus initial kinetic energy. Actually, the work done by the conservative forces include work done by the gravitational force, work done by the spring force, work done by the Coulombic force, and work done by the non-conservative forces includes like friction, viscous force, etc. If there is only the conservative forces, like if there is only conservative forces from the above discussion, when we are dealing with work done by the conservative forces, we get work done is equal to the negative of potential and change in potential energy, that is equal to minus of U2 minus U1. Now we see another important term, potential energy. What potential suggests is possibility or capacity for action. The term potential energy brings to one's mind stored energy. A stretched string possesses potential energy. A compressed spring possesses a potential energy, and a body at a particular height h possess a potential energy. So what potential energy we can define as energy possessed by virtue of its state or position. For example, gravitational potential energy, spring potential energy, these are the examples of potential energy. And we define potential energy as mgh because by the virtue of its position, for suppose it is a gravitational, it depends on the height of the body, so we define this as mgh. And in the potential energy part, basically when we deal with IIT JEE problems, generally they give a potential energy term or a potential energy equation, and then we can equate this to the work, and then we can solve the problems.